Good morning, everyone. Yeah, very good morning. Shall we begin the session? Today I'm going to take the topic that is chapter number 6, Formal Relational Query Language, that is RQL, Relational Query Language. So in this chapter, this chapter we mainly focus on the relational query language, that is based relational model, and the languages that includes the relational algebra, that includes the basis of the widely used SQL languages, relational calculus, and the domain relational calculus, which are declarative query language based on the mathematical logic. So whatever the logic, whatever the relational query we are using out, we are modeling out, we are covering out, that is known as the, or that is covered in the, or that is used in the SQL in greater detail. Now let's talk about the first topic, that is the relational algebra. So relational algebra is a procedural query language. It consists of a set of the operations that takes one or two relations as input and produce a new relation as a result. So whenever it is using the relational algebra, that is a procedural query language that consists of a set of the operations that takes one or more or one or two relations in the sense one or two tables as input and produce a new relation. There is only one relation as output. So it takes either one table, two table, but it produces only one table as the output as the result. And the fundamental operations in the relational algebra are select, project, union, set difference, Cartesian product, and the rename. All right. So let's start with the relational algebra. It's a procedural query language, not a programming language. It consists of a set of the operations that takes one or two relation as the input. That means one or two tables are taken as the input and produces only one output or the new relation as a result. That means only one table is generated as output, but it takes one or two tables as the input. And the fundamental operations in the relational algebra are the select, project, set difference, Cartesian product, and the rename. So let's see what are the various operations over here. So first part is the fundamental operation that include the select, project, and the rename operation. That is sometimes known as the unary operations also. Why unary? Because there is only one operator that is required. One operand will be required for this. That's why it is known as a unary operator, because they operate on the one relation. And only three operations operate on pairs of the relation and are therefore known as the binary operations. So select operation selects the tuple that satisfies a given predicate. So first part is the select. So the selects the tuples, it selects the rows that satisfy a given predicate. So we use the lowercase Greek letter sigma to denote the selection. And the predicate appears as a subscript to the sigma also. And the argument relation is in parentheses after the sigma. Therefore, to select what are the various IDs, what are the various tuples of the instructor relation, where the instructor ID is in the physics department. So we should write sigma department name, that is physics instructor. So if the instructor relation is shown over here, and the relation that results from the preceding query that is given in the that is given over there here, and we find that all the instructor with a salary greater than 90,000. By writing this one. So this is a select, that is sigma, salary is greater than 90,000 from the table instructor. So yes, that's what I'm trying to say, that in general we allow the comparisons using the equals to, not equals to, less than, equals to, greater than, equals to, in the selection predicate in the selection operation. Furthermore, we can also combine the several predicates also into the large predicate that used with the connectives, that may be or, that may be and, that may be not. So therefore, for example, one of the examples we are taking out to find out the instructors and the physics with a salary greater than 90,000. So sigma department name equals to physics and salary is greater than 90,000. So we are taking both these one. One is the department name, that is a physics. One is a salary that is greater than 90,000 from the instructor. The selection predicates may include comparison between the two attributes. So to illustrate, consider the relation department, and to find all the department whose name is same as the building name, so we can write department name equals to building, then department. So department name is building from the department table. Only that output, that means only display the department name, have a building. Your first query is name is physics or salary is greater than 90,000. That means either department name is physics, either the salary is greater than 90,000. Either one of the condition is fulfilled, then the output will be displayed. Yeah, I said either because this is a or. If it is an and, that means it's mandatory to satisfy both the conditions. But in case of or, this is either this, either that. So selection predicate includes a comparison between the two attributes, and to illustrate consider the relation department. To find all the departments whose name is the same as their building name, so we can write this is department name equals to building department. Now next is the project operations. So select operation, select the tuples according to the condition that is denoted by the sigma, then project operation that is denoted by the pi. So suppose we want to list all the instructors ID, name, salary, but do not care about the department name. The project operation allows us to produce this relation, and that is a unary operation that returns its argument relation with certain attribute that is left out. But since the relation is a set, so any duplicate rows are eliminated over here. And any duplicate rows, that means it provides unique data for the unique rows. And since the relation is a set, any duplicate rows are eliminated, that is done, and the projection is denoted by the uppercase Greek letter, that is a pi. So we list those attributes that we wish to appear in the result as a subscript to the pi. The argument relation follows in the parenthesis. That is the same. We write the query to produce like this one: pi, ID, name, salary. So we are taking out the three fields. That means we are not selecting each and every tuple in case of the select, but we are selecting the fields over here. So difference is clear. In case of the select, we are considering the full tuples. Full tuple means each and every record. And in case of the projection, we are considering only the fields. For example, over here, we are considering three fields, that is the ID, name, and the salary. From which table? That is the instructor table. This is the output of this ID, name, and the salary. Only three fields are available, and one more, that is the duplicate records are not coming out. So the fact is that the result of a relational operation is itself, a relation is very important. So consider the more complicated query, that is to find the names of all the instructors in the physics department. So in this case, we are using both, that is the select as well as the project. Why? Because we are taking out some field that is done by the project, but we are putting out the condition, and the condition is put out by the select statement. So we are using both select and the project. How? Like this. This is given over here. This is the pi, then name, then sigma, department name equals to physics. So first of all, we are fetching out the name, then department name equals to physics. We are putting out the condition from the instructor table. So we are taking out department name as physics from the instructor table, and only conditioning of the department name, but the output remains the same, that is the name field. Not the department name, that is only used for the condition. So notice that instead of giving the name of the relation as the argument of the projection operation, we give the expression that evaluates to the relation. And in general, since the result of a relational algebra operation is of the same type as its input, so relational algebra operation can also be composed together in a relational algebra expressions. So composing relational algebra operations into the relational algebra expression, that is like composing arithmetic operations such as plus, minus, divide, multiply into arithmetic expression. Next part is a union. That means combination. Union means combine. Now the next part is a union operation. So consider a query to find the set of all the courses taught in the fall 2009 semester, spring 2010 semester or the both. The information is contained in the section relation, and to find the set of all the courses that taught in the fall 2009 semester, so we should write that is a pi course ID. So we are taking out only one field, that is the course ID, and we are putting out the condition with the help of the select, that is a semester equals to 4 or year equals to 2009. So that is either semester is taken out as a 4 or either the year is taken out as a 2009 from which table, that is a section table. And next is to find the set of all the courses taught in the spring 2010 semester. So we should write pi course ID semester equals to spring or year equals to 2010. So one is a fall 2009, one is a spring 2010. So to answer the query, we need the union of these two sets that is available. That is, we need all the section IDs that appear in either of the, or both of the two relations. So we find this one, that is the course ID, section ID, semester, year, building, room number, and the time slot ID. So one is the bio, that is the course ID, section ID 1, summer 2009, and the painter 514. So it is taking out two things. One is the spring, one is the 4, 9, and the 10. Now these are the summer, fall, spring, fall, spring, fall. Yes, you can combine two queries also by using the union sign. So this is the ID, or taking out the course ID, then semester equals to 4 and year equals to 2009 from the section. It is merging up with the union sign. It is merging up with the next one, that is the spring 2010. Yeah, whole table comprises fall as well as the string. No. It does not eliminate the duplicate data. Why? Because we are not using any. We are not using any distinct keyword over here. Now, next part is a set difference. So, any doubt in the select, any doubt in the project, any doubt in the difference among the select in the project. Next is the set difference, that is denoted by the minus sign. That allows us to find the tuple that are in one relation but not in the another relation. For example, suppose one table contains 3, 4, 5, 6. Listen, 3, 4, 5, 6. Another tuple contains only 5 and 4, or 4 and 5. So what is left over? That is a set difference. That is in the A but not in the B table. That is 3 and the 6. That is denoted, or that is known as a set difference. The set difference operation denoted by the minus sign that allows us to find the tuple that are in one relation but not in the another relation. And the expression R minus N S produces a relation containing those tuples in the R but not in the S. That is the same. So this is CS 347 PH510. The courses offered in the fall 2009 semester but not in the spring 2010 semester. And we can find all the courses taught in the fall 2009 semester but not in the spring 2010 semester by writing this one. This is our course ID, semester equals to fall, year equal to 2009, section. Then course ID, semester equal to spring, year equal to 2010, section. So both contains the table, that is a section. And the result relation for the query that appears over here, this is the output of this. Next is the Cartesian product. Alright, so read out, select project and the set difference. If there is any doubt, then please ask the doubts. Yeah, this Cartesian product is denoted by the cross sign, that is a multiply sign. Okay. Now the next part is the Cartesian product operation. It is denoted by the cross sign. That is the first thing that that allows you to combine the information from any two relations. Suppose there are two tables and I want to join these two table information from any two relations. So we write the Cartesian product of the relation R1 and the R2 as R1 multiplied by R2. That means two relations are combined. Each and every row and the field are combined by using the Cartesian product, that is R1 multiplied by R2. And recall that a relation is by definition a subset of a Cartesian product of a set of the domains. And from this definition, we should already have an intuition about the definition of the Cartesian product operation. However, since the same attribute name may appear in both R1 and the R2, so we need to devise a naming mechanism. Naming mechanism means we need to give the new mechanism, that is R1 and the R2. We need to devise a naming mechanism to differentiate between these attributes. And we do so here by attaching an attribute to the name of our relation from which it is used, from which it is defined, or attributes are generally or originally came out. For example, the relation schema for R equals to instructor into teacher is instructor.id, instructor.name, instructor.department name, instructor.salary, teachers.id, teachers.course ID, section ID, semester and the year. With this schema, we can differentiate, we can distinguish between the instructor.id from the teacher.id. And for those IDs or the values that is using out with the two schemas, we shall usually drop the relation name prefix. And the simplification do not lead to the ambiguity. Now we are talking about the two tables to attribute relation schema, that is instructor into teachers, that is instructor.id, instructor.name, instructor.department name, salary, then teacher's ID, course ID, section ID, semester and the year. And with this schema, we can differentiate instructor ID from the teacher's ID. And for those attributes that appears in only one of the two schemas, we shall usually drop the relation name prefix. And this simplification does not lead to any ambiguity. So we can then write the relation schema for R as instructor.id, name, department name, salary, teachers.id, course ID, section ID, semester and the year. This naming convention requires that the relations that are the argument that is used of the Cartesian product operation have a distinct value, distinct names, and the requirement causes the problem in some cases, such as when the Cartesian product of a relation with itself is desired. Similar problem is used with the result of the relational algebra over here. This is the teacher's relation. So this is the R equals to instructor into teacher. The tuple that appears over here, that is not this one. And this is the output of this query. Next is the rename operation. Rename is denoted by the row, that is phi, and that the result of expression E under the name X. And the relation R by itself we consider as the A, that is a trivial relational algebra expression. Therefore, we can also apply the rename operation to R to get the same relation under a new name. And the second form of the rename operation is as follows. Assume that a relation is algebra expression E as a Rtn. Therefore, the expression phi x a1, a2, an e returns the result of an expression E under the name X, with attributes renamed to the a1, a2 till an. And to illustrate the renaming of a relation, we consider the query, find the highest salary in the university. So our strategy is to compute first a temporary relation consisting of those salaries that are not the largest. Take out the set difference between the relation pi, salary instructor, and the temporary relation just computed to obtain the result. And next is step number 1. To compute the temporary relation, we need to compare the values of all the salaries that is used by that is computing the Cartesian product, that is the instructor into instructor, and forming a selection to compare the value of my two salaries appearing in one tablet. First, we need to devise a mechanism to differentiate between the two salary attributes. So we shall use the rename operation to rename the salary attribute. This is the instructor.salary, then instructor.salary and the d.salary, that is combined with the instructor. Now next